Good morning, everyone. We're going to get started here now. Today, we'll be talking about using the CTs with the inverter, um, what you use them for, how to install them correctly, and the limitations and what you can do with them. Talk about which cases we use them for, when we have to use them, when we don't use them, where do we put them, and what do they do, and how to install them correctly, because this is actually major problem we see is incorrectly installed CTs, and it can cause some really bizarre inverter behavior when they're not installed correctly. And there's some limitations on them, and we'll talk a little bit about the CT smart meter that resolves some of those limitations, and we're just starting to roll out the smart meters. When we use them is anytime we're doing a system in self-consumption mode on the inverter. This includes most grid tie systems, as we discussed previously. Generally, we're using self-consumption mode on the inverter for grid tie systems, even ones that are doing mostly just battery backup net metering. We're still doing it in self-consumption mode, just with a really high reserve state of charge. If you use in off-grid mode, you do not need the CTs. And if you're doing grid feed in with no batteries, then you may or may not use the CTs, but that's a pretty limited case where you'd be using the grid feed in. Just about all of our grid tied systems are going to be used in self-consumption as the operating mode. So we're going to be using the CTs on those. The CTs allow us to do zero export or limited export if we have limitations on our grid connection. It also allows us to support normal loads at nighttime with or without zero export. So say we've got net metering, but we've got a time of use rate at night, and we want to operate loads from the battery at night, but not export the batteries to the grid. The CTs allow the inverter to see what's going on and power those normal loads without exporting the battery to the grid. If we look at kind of a typical setup here, we've got our inverter. Here we've got our backed up loads here on the inverter AC out. And then our normal loads are all the other loads in the main panel that are not backed up by the inverter, sort of our non-backed up loads. So say we want to power these normal loads here, we need to know how much power are they drawing so the inverter can send just enough power back through its connection to the backfed breaker here to power those normal loads, but not sell to the grid. So we've got our CTs monitoring how much power is coming in from the grid, and we can tell exactly how much that inverter needs to push into there to support those normal loads. Or say this is a zero export situation. We want to make sure we don't export to the grid, so we monitor that connection to the grid. And during the daytime, it's powering the backed up loads here, but it can also power these normal loads without exporting to the grid. And similarly, if we've got a limited export to the grid, where say maybe we've got a 6 kilowatt cap on what we can export to the grid because of feed lines or transformer sizing or something from the utility, we can say limit the export to the grid to 6 kilowatts, and it will look at those CTs and adjust to do that. So those are kind of the cases where we might be wanting to do something that really needs these CTs to tell the inverter what to do. Placement of the CTs. This is the same diagram we were just looking at, and kind of in the manual for the inverter, it kind of shows it right on these feeders going into the main breaker. If you can get access to those feeders, that's kind of the preferred location for it. We program it. We'll talk about the programming a little bit after we go through some of the diagrams and the installation. But in programming, we want to program it to grid side for the sensor location and set it to energy flow direction from grid to inverter. That's the direction these arrows are pointing here. This is our preferred connection, but we get a lot of interconnection setups that are a little bit different. Maybe we can't do a backfed breaker because of our 120% rule, and we've got to do a supply side tap. So now we just have the CTs kind of on the grid side of that tap up ahead of that main breaker. Electrically, it's the same as it was before. We're measuring that power going in and out of the grid, kind of on the grid side of all the distribution where it breaks into loads and inverter connection and such. So this is another common one we see. Another common one we see is an all-in-one service where the meter and the main breaker are connected together. We can't get access in between there. Most utilities don't allow you to open up the meter cabinet and put CTs on the wires in there, because that would be a electrically perfectly fine place to put it, is on the grid wires coming into that meter. But most utilities say, no, you can't be putting customer owned metering inside of our meter cabinet. So we don't have access to those wires right there. So here's one way of doing that. We just put the CTs on the wires coming from the breaker panel to the inverter AC in. Now we have some functionality. We don't have as much functionality as we did before. The inverter, it can still see how much power is coming in here, and we can do zero cell or limited cell, but it's not truly measuring what's happening at the grid. It can't see any of these normal loads here. So if it says I've got a limited cell right here, maybe that's limited to 7,600 watts because we've got a 40 amp breaker limitation right here. It's a 200 amp panel. So we can say we're limited to 7,600 watts here. That doesn't mean that we're exporting 7,600 watts to the grid, because these loads might be using up quite a bit of that power. And that's just a limitation when we've got the CTs at this location. Similarly, if we said we've got a zero export, we are not allowed to export to the grid. If we've got our CTs in this location, it'll do zero export to this loads panel. That means all of these loads here are always drawing from the grid. Only the backed up loads are being powered by the solar. So that could be a major limitation depending on what the ratio of our normal loads to our backed up loads is. And also on the app, when it's showing here's the load from the grid, here's the production from the solar, it's not going to catch any of these other loads here. So it's going to give you an inaccurate number for what the total load from the grid is, because it can't see that. It's only seeing the amount coming to the inverter from that breaker, not the whole thing. So this is a very common situation we run into, and it does have a lot of limitations when we can't get the CTs on that feed in between the meter and that main breaker. Now, there are some ways around that. Here's kind of a common situation where, go back to that picture. There we go. Here we have kind of a common one where there's a meter main on the outside of the building, and kind of, I show it as a sub breaker here, but often it's the feed through lugs in the bottom of this panel that goes into an indoor panel. So there might be a load on this outdoor panel, but often it's just feed through lugs going to a indoor panel. In that case, we can put our CTs on those wires going to that indoor panel where all the loads are, and we can measure those loads. We still are blind to these loads, other loads plugged into this outdoor panel here, but we can measure the majority of the loads here. And in this case, we set our sensor location to load side and our energy flow direction from grid to inverter, which is really not an accurate description of how the arrows are pointing. They're pointing from load to grid, but that's how you program it to make this work. And that's a way of dealing with when you've got kind of an all-in-one service, which is just really feeding a feed through to most of the loads. Depending on if you have no loads in the outdoor panel, this can be just as accurate as getting the CTs up here above the meter. If you've got some loads in this outdoor panel, those are still going to be ones that the inverter is blind to. It won't be able to do support normal loads with those, and it won't add those loads into kind of its grid total that it's showing on all the metering on the graphs on the app and stuff. Another way to do that is CTs. You can run more than one wire through a CT, and it just measures the sum of all the currents going through that wire. So we can take the output wire from the grid to our inverter and actually run it through that same CT that the load feeder is on. It's big enough to fit a 4-aught plus our 2 gauge going over to the inverter through that one CT. And now it's measuring the sum of both those currents. Electrically, this is actually as if that CT was slid all the way up to the main output of this main breaker before those two currents diverged. So it's just as if we had our CT on this main going back to the grid, even though it's actually two wires we're measuring after it's split. So that's another way we can set it up as if we were on the grid side. It's electrically, it is on the grid side. It's just kind of splitting and then going through the CT as two separate wires, but it's still the same current as if we were measuring one wire on the grid side. And then we set our energy flow direction from grid to inverter just as before. So that's a way we can do it when we have these feed through panels. Again, if we had a load breaker here with something else pulling off of this little bus bar in here, usually it's an 8-space panel. If we had another breaker here, we would either take the output of that breaker and also run it through that same CT in order to see that load as well. Or if we couldn't fit it through there, we'd just end up being blind to that particular load and have that limitation like we discussed before. When we look at our CTs that come with the inverter, they are labeled for which phase they are, and it's very faint, you can see here, L1 and L2. So it's not, you have to take a look at it in good light. I might even like mark them while you've got good light before you get into some dark little box where you're trying to stick them in there, and make sure you know which one is which, because it's very important which one is L2 and which one's L1. It's letting the inverter know what's going on each of the two phases, and if they're switched, it would be like getting in your car and you turn the wheel left and it turns right, and you turn the wheel right and it turns left. That'd be very hard to drive. Inverter has the same problem. If L1 and L2 are switched, it doesn't know which direction is which when it's looking at things, and it can't accurately control what it's doing. How do you verify for sure that L1 and L2 are correct? The best way to do this is to take your voltmeter, and in this graph here, or this figure here, measure between 0.1, that wire right where it goes into the top of that circuit breaker, and you can see you've got the CT clamped on that exact wire, and then measure over to 0.2, the actual input into the inverter. Make sure that you have 0 volts from 0.1 to 0.2 here. If you measure that with your voltmeter and you've got 240 volts, that means somewhere between 0.1 and 0.2, you switched the phases. Often where that happens is if you can't really see that bus bar behind all of these breakers really well, you may not be able to tell, is phase two the lower terminal or the upper terminal on that breaker. It might be different depending on the exact bus bar layout. Also, we have seen main breakers here where it actually crosses the two phases going through the breaker. So it physically looks like L2 comes down here on the right side and therefore should be the right side output. But we found some main breakers where it crosses internally and the right side input comes out of the left side. So just looking at it is not always enough to tell which is line 2 and which is line 1. Actually measuring it with a voltmeter is what you may need to do. Now, sometimes your main panel where you're putting these CTs, it might be on the other side of the house or the other side of the garage from your inverter. You can't get your voltmeter to measure from 1 to 2 because the leads aren't long enough. In that case, what you might have to do is measure from 1 to 3. So basically verifying how it goes through this whole assembly and which one's coming out of your feed breaker here. And then use color-coded wires going from 3 to 2 here to make sure that stays in sync. So you might have to measure in a couple stages rather than just measuring directly, but make sure that you've got your phase 1 and 2, and in three-phase systems, you got to make sure 3 phases are all correct. Otherwise, the inverter's all confused and doesn't know whether to turn right or left if you switch those two CTs. Another detail of the CTs is which way is that arrow pointing. Here's where the arrow is embossed in the inside of the CT. And there it is embossed slightly less distinctly on the outside of the CT. You might want to get one of those silver, like Sharpie paint markers and make these a bit easier to see, both the L1 and the L2 and these arrows, before you go into a little dark box to snap them onto the wires to make sure that they're correct, because they can be a bit difficult to see once you really get in there in your tangle of wires putting these around there. This is also very important to get correct because it's as if you're driving the car again and reverse and forwards in the car got switched. So you try to drive forwards, and instead of forwards, the car starts moving backwards. Well, the inverter's response to this is to say, I'm not moving forwards, I need to give it more power. So because it's going the wrong direction, it essentially floors it in reverse if it's switched. So what we often see when these CTs are facing the wrong direction is really bizarre behavior, like the inverter will dump the batteries into the grid at the full 10 kilowatt rating of the inverter as fast as it can because it's trying to do zero export. And if the CTs are reversed, it keeps thinking, I need to put more power in to get the export to zero because I'm exporting power. And it puts more power in. And it gets confused because everything is feeding back to it the wrong direction. So often when you see really bizarre behavior, and especially the inverter dumping the batteries to the grid, that's a sign that the CTs are reversed and pointing the wrong direction. Now, if both CTs have the arrows pointing the same wrong direction, it is possible to switch that in the software. But if one of them's the wrong direction and the other one's the right direction, there's no way to fix that in the software. You've got to fix that physically in the installation by having them snapped on there the right direction. So this is probably one of the problems we see in, I don't know, a lot of the cases, very common issue with CT placement is that they're on the wrong lines or facing the wrong directions. So really remembering that both getting L1 and L2 absolutely correct and double checking that and making sure the arrows are facing the right direction will solve probably 80% of the problems we have with CTs is just not paying attention to the placement. They are a lot more picky than a lot of people assume they are. It's like, oh, clip them around a wire, it'll be fine. It's got to be the right wire in the right direction. Going into programming the CTs, we discussed before that obviously self-consumption mode is when we need the CTs. If we're doing off-grid mode, we don't need the CTs. We'll just set them to be disabled on the next screen. But when we're in self-consumption mode, that's when we need the CTs. We can have support normal loads on or off and zero export on or off. If we're not doing zero export and we're not supporting normal loads, you might think, well, those are the two things that I need the CTs for. But just the way the whole inverter is programmed and stuff, you do need the CTs when you're in self-consumption mode, even if you're not doing either of those things where it's really needs the CTs, because it's expecting to be able to see the CTs if it's in self-consumption, even if it's not doing either of those functions. Under power control, we want to set it to CT sensor. If we're using the smart meter, we want to set it to smart meter. We'll talk about that in a little bit. So if we're using the CTs that come with the inverter, then we want to set it to CT sensor. This is also where if we're doing off-grid mode, we would do disable, and then we don't have to use the CTs, and it doesn't give us any errors or complaints about not having CTs if we set it to disable. But if we're in self-consumption mode and we set it to disable, then we're going to get all kinds of weird results if we don't have our CTs on there. And we can set our sensor location, usually on the grid side, but as I showed in that one diagram, it is possible to do it on the load side. And I will put up a PDF of this so you have those diagrams with how to program each case available. I'll send it out an email about that later today with the link to the PDF so you have those diagrams available. We'll also be getting this recording of this webinar up on our new YouTube channel, which I'll be sending out in that email later today too. And then energy flow direction, usually from grid to inverter, but if we've got the arrows facing the wrong direction, this is where we can switch that in the software from inverter to grid. Now, if we're on the load side, these are the same things, and they don't quite have the same meaning. You just need to go off of what the diagram says it should be for a given arrow direction rather than thinking about, because it's not actually pointing from grid to inverter if it's on the load side, but you still only have these two options for what to program it to. Limitations of the CTs. They're about a 1-inch throat on them, which means they're good for a single conductor up to 350, maybe 500. So generally anything you'd see on a 200 amp service. Or if we're doing kind of that outside feed through panel and we want to feed a couple conductors through there to get all of them visible, even though we can't get on that grid side conductor coming right out of the meter, we can fit a 4-aught plus the number 2 and maybe some other ones in there with some kind of playing around with the wires to get them all in that rectangle. We're limited to a 200 amp measurement on the CTs that come with the inverter. There's only 2 CTs. We can't do 3-phase when we're doing CTs directly connected to the inverter. We can only do split phase. One thing to mention is when we have stacked inverters, only the master inverter gets CTs. So we don't put a set of CTs on each of our different inverters. We just have one set of CTs on the master inverter, and it kind of is the brain that controls what the other ones are doing based on what it's seeing on its set of CTs. The CTs come with a 15-foot cable. If you're mounting your inverter right next to your main service, that's probably fine. If you're on the other side of the house or the other side of the garage, that might not work. You can extend the CTs with a Cat6 cable and good quality RJ45 couplers, but the accuracy can vary because it is an analog signal on those. And also, we've had issues with a lot of the cheap couplers and cheap cables having issues with that. And we really don't want the CTs dropping out of communication with the inverter because it starts doing bizarre things when it can't see what's going on. So we want to usually limit that to about 100 feet. We've had people do a 200 foot with a really nice Cat6 cable, and it seems to work. The accuracy might not be perfectly there, but it seems to work fine. But in general, we recommend no more than 100 foot and get good quality Cat6 cable and good quality couplers to extend that. We don't recommend just cutting the cable and extending it because we've had too many cases where people have miswired it when they've cut it and tried to couple it together. And then nothing works correctly. So if you're going to cut it, make 100% sure that you keep each wire going through correctly. Otherwise, it's just not going to work. We recommend using the Cat6 cable with couplers. That way it'll keep going through there. The CT smart meter. This is an extra accessory that we're just rolling out. We have a couple of these in testing right now, and we should have more in a month or two, hopefully. This one, essentially it's a standalone meter which measures power on 1, 2, or 3-phase systems. It can do 1, 2, or 3 CTs. And so you'd use 2 of them for a split phase system or 3 for a 3-phase system. So this allows you to do self-consumption mode in 3-phase, whereas previously we were limited to only off-grid mode in 3-phase. So this adds that ability to interact with the grid and do self-consumption in 3-phase. We get larger CTs. Right now, we still only have 250 amp CTs with a 1-inch throat, so really no larger than the CTs that come with the inverter. But we're working on getting some 600 amp ones that'll have a 2-inch throat. So when you've got a 400 amp service and you're doing a stacked set of inverters on that, and you want to be monitoring that whole 400 amp service for purposes of zero export or supporting normal loads, you'll be able to get that around those usually parallel 4-aughts or parallel 250s coming into that 400 amp service. There's another workaround that we're also working on right now, but probably be best to wait for the 600 amp CTs for that. So this meter, it communicates digitally back to the inverter rather than an analog signal going back. So there's a bit longer extension we can use, up to 300 feet away from the inverter. So if you've got a service that's just farther away from your inverter setup than the 100 feet kind of recommended limit for extending the CTs, you can use this smart meter and send the information back to the inverter. Now this smart meter, it needs a separate box. This is about a 4-inch square, a little DIN rail mounted thing, and it needs a separate waterproof box for it to be in. If you've got a lot of room in your main service panel, you could mount a little piece of DIN rail and mount it in there. Most of the service panels I see do not have lots of extra room in them. So you may be having to get a separate little NEMA 4X 8x8 box to mount this in out by the service if you're connecting it. So that's a thing to consider when you're using the smart meter is that it's often going to require this extra little box for somewhere to put it. And that is what I've got on CTs for now. Do we have any questions? I'm not seeing any questions, so I'm going to wrap up. Oh, maybe we do have a question. So I'm going to wrap up, and we will, like I said, I'll email you the new YouTube channel, which I am putting up videos of all of these presentations so you can refer back to them. And also, that's a place you can see them if you're not able to attend this time. It's hard to find a time that works for everyone in multiple time zones, and some people can only do it during business hours, and some people can only do it after business hours. So, getting them up on the YouTube channel will be good for that. Um, Also, I'll be just reminding everyone of the link to the shared drive where we have different technical documents for assisting things. I'll have the PDFs of these presentations there if you want to print out some of the diagrams and things showing where the CTs go. And we will see you next week. I will not sure what the topic will be next week, but I'll try to include that in the email later today once we decide what next week's topic is. If you have ideas for what you'd really like to see a training on, please email me because I'm putting the next couple weeks of training topics together this afternoon and want to see what people want to see after what we've already covered the last few weeks. Okay. Thanks everyone. We'll see you next week.